Alright, so welcome to week 4, ELEC 3067, 26th summer electrical machines class. Yeah, London, Ontario, Fanshawe College. Okay, today we'll talk about certain phenomena that I was meaning to talk to you about for some time now. So today is the day. All right. And here is the topic. The topic is, excuse me, understanding magnetic permeability. How materials respond to magnetic fields. Right, so we just have the good old version of a permanent magnet here with a north pole and a south pole, and there is this distribution of the magnetic field lines, and outside of the magnetic source, which is the permanent magnet here, we have the lines. Well, they should be coming out. Okay, well, I just noticed here's the artificial intelligence for you. All right, the lines should be going this way here, like that. All right, from the north to the south. You see here they are like that. All right, and for some reason the other ones are. Yeah, thank you AI. All right, don't believe everything you see. Yeah. All right, so on the outside, the magnetic fields flow from north to south, and of course, to complete the line, they will be flowing this way here inside the magnet, just like the power supply idea, EMF versus voltage drop. All right, magnetic permeability or permeability. Magnetic conductivity in reference to specific materials. So this is the sort of definition page. What is magnetic permeability? Is the magnetic conductivity in reference. Well, we're going to reference that to specific materials. Magnetic permeability measures how easily a material supports the formation of magnetic field within itself. So how easily it passes through, or how easy, well, passes through. Certain materials can pass the magnetic field through, but not react. But the key idea is, how is it that those specific materials support the formation of magnetic field within, well, that material. Magnetic permeability indicates how effortlessly magnetic field passes through a material. That also. That comes with something that's called shielding. All right, Faraday's cage comes to mind. And when the permeability is high, it means that the material concentrates the magnetic flux. And here is the good old highway analogy. We have two cars. The car on the left is driving on a dirt road, and the car on the right is being driven on smooth pavement, which is the road made for cars to drive on. Which is easier for the car? Well, of course, the answer is the one on the right. We will expand that idea as we go along here. All right, magnetic flux. I just thought I would give you this presentation in the context of what you're going to be doing in the lab this week, which I think the lab is as far as I remember. It is the DC generator, and we will be magnetizing certain things there within the motor or within the machine, DC machine. And we see how far we can magnetize it before some things happen, and you will find out what that thing is. All right, we're talking about magnetic flux. For the magnetic flux, in the permeability in the context of magnetic flux, high permeability concentrates the lines of magnetic force lines. Low permeability allows them to pass through without any concentration. All right, so here's one key idea here. Another, magnetic conductivity. Objects or materials with high permeability characteristic conduct magnetic fields easily, conduct magnetic fields instead of just passing them through. There's a bit of a difference. And low permeability objects, they act as poor conductors for magnetic field. Doesn't mean they are not going to pass the magnetic field. It's just they're not going to behave certain way. And also we're going to expand on that idea as we go along. Material examples. High permeability objects include something like iron, nickel, and mu metal. Right. That should be, well, mu, and also could be the Greek letter mu. That's how you read mu. Low permeability include air, water, copper, wood, vacuum, but vacuum is a special case. Then in the context of magnetic flux, I'm going to concentrate. Oh, well, this thing is a repeat here. All right, cool. So you get this thing twice. What is mu metal? Mu metal, or the mu metal, Greek letter mu, because I listed that here, so I thought I would explain that. What is it that I mean by this? A mu metal, or the Greek letter mu metal, is a specialized nickel/iron soft ferromagnetic alloy engineered to have exceptionally high magnetic permeability. So what do we have here? We have North Pole and South Pole. 3 scenarios. Here is air or vacuum, and we have just uniform lines going through. Then we have something that's called copper with low magnetic permeability. Copper will pass through the lines, but will do not much to them. Now look what happens when we pass the magnetic field through iron. Right? Iron is a magnetic material. Magnetic material concentrate the field lines. They kind of just look like a lens in photography, right? So that's the idea of the permeability. That's what happens. That's what I mean by the previous slides. Previous slides. High permeability conducts easily, and with high permeability, high permeability objects concentrate the lines of the magnetic field, and this is how things are happening. All right. For the mu metal, typical composition includes nickel, about 75% to 80%, and iron, and then there's some other trace elements, small percentage of molybdenum, copper or chromium, improve the structural magnetic properties and magnetic properties. Applications. Well, the phenomenon in of permeability is used in high-stake technology environments where stray magnetic field can corrupt data or sensors. So with this statement here, we're talking about shielding, preventing magnetic field from entering certain areas. Now, did we study the coaxial cable with me or with somebody else? There is a ferric type of a shield around the coaxial cable, which prevents from the interference, electromagnetic interference from getting through to the signal. All right, medical equipment, that's also shielding, aviation or space, and with some precision electronics, all these here, they're talking about shielding here. We also use, when we had the class, the in-person class earlier this week, we talked about transformers. That is also now, with the transformers, we want them to concentrate the core, the ferric core. Ferric comes from ferrum, which is iron. They help to guide. The ferric core helps with the guiding of the magnetic field lines in a way that they can be guided efficiently wherever we want them to go, which is basically past the magnetic field of as much as we can of a concentration to the other windings or the other coil that is around, wrapped around the other ferric core. What else do we have here? Magnetic materials like iron concentrate and redirect magnetic fields away from sensitive equipment, so that will be the shielding. This process creates a protective barrier known as magnetic shielding. Shielding prevents external magnetic fields from disrupting sensitive devices such as, for example, MRI scanners. That would be the medical equipment. All right, here's a page full here. Magnetic permeability in the context of, that is, material's ability to support the formation of magnetic field within itself. So we talked about that here. We got a couple of images. Here is a coil wrapped around nothing, just thin air or a vacuum. And here is a coil wrapped around a ferric core. Ferric core is considered as ferromagnetic material. All right. So again, let's go back to this thing here. Magnetic permeability, material's ability to support formation of magnetic field within itself, acts as magnetic conductivity. The magnetic permeability acts as magnetic conductivity, measuring how easily the magnetic lines can penetrate and flow through the substance, which in this case we have a piece of iron. All right. Materials respond to the magnetic field in three different distinct ways. We distinguish ferromagnetic materials, paramagnetic materials, and diamagnetic materials. That kind of seems like this word, dielectric, for electricity. Dielectric is an insulator. For magnetic field, diamagnetic is, something that would prevent or act as a shield. All right. Ferromagnetic materials, highly permeable or permeable materials like iron, nickel, cobalt, readily concentrate magnetic flux strongly attracted to magnets. Physically, we got a physical attraction to magnets. They support formation of strong internal magnetic fields. Look at these two pictures here. Here is a coil wrapped around nothing, and here's a coil wrapped around a piece of iron. Over here, the magnetic lines, they go from north to south on the outside and from south to north on the inside. And they form kind of like a natural uniform pattern here. Now, what happens if we stick a piece of iron inside that coil? Those magnetic fields are going to highly concentrate in that, because that is acting. That ferromagnetic material acts as a nice, smooth, paved road for this car, as opposed to just any kind of surface, not necessarily designed for driving. Or maybe driving, but not as efficiently. Right, so here's the idea. We're talking about the permeability. There's also permeability is a term that you're going to hear in other branches of science or construction. Like, for example, when you're talking about the vapor barrier in the buildings, and why am I telling you that? Well, some of you might find a job within the industry of maybe running some wires and drilling holes through the walls and things like that, and that has to do with disturbing the vapor barrier that separates the inside of the house with the outside of the wall. And we're talking about the permeability, but not this magnetic permeability. We're talking about permeability of the wall. How permeable the wall is, which means how is it that the wall lets the house breathe. And when we are talking about running wires and disturbing especially disturbing the exterior walls, where they have to have the vapor barrier, you might want to research that, then you can do a lot of damage. You might know a lot about electricity, about other things, but then if you disturb the wall in the wrong way, and if you don't patch it up or repair it in a proper way, then you might install something that is going to work properly, but you're going to cause a lot of damage. And the word black mold comes to mind. So permeability of the walls, it's a different permeability than the permeability that we're talking about here. Right? We're talking about the magnetic permeability. Right? So ferromagnetic materials, again, highly permeable. Iron, nickel, cobalt, they concentrate. They're like a highway, like a conductor for the magnetic field. And they support the formation of strong internal magnetic field here. Paramagnetic materials such as aluminum or aluminium if you're in UK, magnesium, tantalum, their permeability is slightly greater than the permeability of the vacuum. Only slightly attracted to magnetic fields. They do not hold magnetism when external field is removed. So you can magnetize a nail or a screw because they're made out of iron, for example, and you can magnetize a screwdriver, which is some kind of an iron steel alloy, and you can magnetize that, and you can pick up some screws with that, and it's going to stay. You can also demagnetize that. Right? You cannot magnetize aluminum. Okay. Then there's the diamagnetic materials. Materials like copper, water, gold, for example. Their permeability is slightly less than the one of a vacuum. They actually repel magnetic fields. and they have a weak, negative response to them. To what? Them, to the magnetic fields. There's the funny picture here. Again, the artificial intelligence kind of drew those. I requested a picture of that. I didn't notice that. This is correct, and this is not correct. Okay. What is the baseline and what is the unit for permeability? Well, we have to have some sort of common ground, like a baseline. What do we have as a baseline for our electronic or electrical instrumentation or systems or circuits? Well, we do have ground. Anything voltage that is greater than the ground level, we consider that as positive voltage, and anything that's less than what we establish as a ground, we consider that as negative voltage. And as far as current can flow one way and the other way, depending on where the voltage is at the moment, at what level. So we need to have some sort of baseline, same for the permeability. And our baseline is vacuum. In a perfect vacuum, or empty space has no atoms. We're talking about perfect vacuum, the perfect nothingness. Right. Magnetic field can still travel through it. But this baseline is called the permeability of free space, and we call that mu0, with the designation of mu0, a Greek letter mu. Now, what will be the value of that? Here's this here. Notice the unit of the permeability is henries per meter. So that comes down to, I'm not going to derive where the 4 pi comes from, but you might want to kind of write it down, remember this, or know where to look for it in the future. The permeability of a free space, which is our baseline, our reference point, is 10.26 times 10 to the negative 6 henries per meter. All right, so that's the unit. We got the unit. We got some values happening here. All right. What did I write here? To understand how materials affect magnetism, we must start with no material at all. All right, so we have the coil wrapped around nothing. In vacuum, magnetic field travels with zero interference. Interference, positive or negative interference. Nothing is affecting those. Right? We measure this baseline using the constant called mu0. So that's our baseline here. That's our sort of like a ground level for electricity. But this is not electricity. Well, sort of, but we're concentrating on the magnetism part. All right. Somebody drew this. There's something here. I wonder if somebody has access to the pan here. Am I supposed to be the host here? No big deal. All right, let's keep going. Huh, that's weird. That thing just stayed there. Alright, now here we have an object. And we have another object. And we're talking about, what are we talking about here? Remember here? Oh, here's the slide. We're talking about ferromagnetic materials, paramagnetic materials, and diamagnetic materials. If we have an object that is exposed to magnetic field, those lines here, those blue lines here, there will be a magnet, will be here, north and south, and that object will be put between those. If it's a ferromagnetic, right, let's just write this. Let's just read what it says here. This image represents the magnetized state showing how the atomic magnets align, because atoms can be compared to miniature magnets, right? And they would have north and south, so there will be they will have vectors pointing north and south, or the force. Okay, so this image represents a magnetized state of, so something can be magnetized, or here on the left is something that is either not subjected to the magnetic field, or it could be subjected to the magnetic field, however, it doesn't care. This one does care. So this, obviously, it says that this is a ferromagnetic object. This one here could be ferromagnetic, not exposed to a magnetic field, or it could be, if it's exposed and it looks like this, then it could be paramagnetic, which means it doesn't care. It might still pass the lines through, but it might not react by aligning itself, and thus helping conduct the magnetic field. Alright, let's go back here again. This image represents the magnetized state of showing how atomic magnets align when external magnetic field is introduced. Applied field represented by the blue lines, the blue paths here, pulling the atomic magnets into uniform alignment. The ease with which these arrows pivot and line up defines the magnetic permeability. The ease in which it happens, with which it happens, defines the permeability of that specific material. When we introduce a solid material into magnetic field, things change. The material isn't passive. The atoms inside have their own tiny magnetic fields that will either help the magnetic field, or they will ignore the magnetic field, or fight the outside magnetic field. On this one here, what does it say here? The red vectors in the image represent atomic magnetic dipoles. There is not a monopole when it comes to magnetism. If you have a magnet that has a north and south pole, if you cut that right split in the middle, you're not going to have a north pole and a south pole separate. You're going to have two objects with each having a north and south pole. The red vectors in the image represent atomic magnetic dipoles. All the atoms, they act as mini magnets which have dipoles, which means they have north and south. They are often called atomic magnets or microscopic magnetic moments. All right. Microscopic currents. Each arrow represents the net magnetic effort. Sorry. Each arrow represents the net magnetic effect of an individual atom created by the spin of orbital motion of its electrons. And we're not going to get into how exactly the atom looks, because there are debates on that as well, but we're not getting into that. Now, here's the concept: net zero magnetization. Because the arrows point in random directions, their magnetic fields cancel each other out. The material has no overall microscopic magnetism on its own. And here's the baseline state. This depicts the material before it is introduced to an external magnetic field. And once we introduce that, if it's a ferromagnetic, those domains, those miniature magnets, those miniature atomic magnets will align if it's a ferromagnetic, and they're going to work with that. They are going to make that pavement for the magnetic field. They're going to make that road, the paved road for a car. So of course, if you build a road, that's where you're going to get all the cars choosing to drive by, not on the grass beside it, right? Okay. Just like that. Permeability tells us how welcoming a material is to magnetic flux. High permeability, just a repeat, but we're going to drill that. High permeability materials act like a highway for magnetic fields, forcing the field lines to bunch up inside them. And of course, as I said, if you have a bunch of cars, of course they're going to choose driving on the nice smooth pavement instead of driving on the median there. Again, what are the three magnetic material types? Ferromagnetic, paramagnetic, diamagnetic. Again, ferromagnetic are massive multipliers of what? Of the magnetic field. Atomic magnets align perfectly to strengthen the field. Example will be iron. Ferromagnetic materials love magnetic fields and multiply their strength. Paramagnetic, weak helpers. Atomic magnets align slightly, but paramagnetic are neutral or positive. They are pretty much neutral. They don't care about the magnetic field passing through them. And diamagnetic, weak. Oh, there's a spelling here. Resistors, resistors. Atomic magnets push back against the field. They will oppose actually here. For example, copper. I wish I had show you the ring, magnetic ring. Slide over a copper rod, see what happens. Maybe I'll find a video. Diamagnetic materials fight the field. Alright, now here is a coil. Let's say this one would be, well, let's say we choose this top one to be the primary winding, and we choose the bottom one to be the secondary winding of a transformer. And I would say, which material would you use to produce the core for this transformer? Would you use ferromagnetic? Would you use paramagnetic? Or would you use diamagnetic material? I'm pretty sure everybody knows which one would you actually feel? What is the idea of a transformer? That we actually talked about transformers last time in our in-person class. The idea is to induce the voltage in the primary, from the primary to the secondary coil. So if we want to induce the voltage, you need to affect that coil or the windings or the conductor that's wrapped around with magnetic field. And when you are applying voltage here, AC voltage, to these two terminals here, these two terminals here, introduce the voltage here, AC voltage, it is going to cause an alternating magnetic field, which we want to be passed on to the secondary. So this could be one, if it's primary, and it could be secondary. But we want this thing to be done as efficiently as possible. So if we use the ferromagnetic material, that will help you guide the magnetic field. It's going to go back and forth because it's AC, so I'm not drawing any lines, any arrows on those lines. And if we use that as a basically helper to guide as much of a concentration of the magnetic field, then we're going to have something that's called an efficient transformer. And as we talked about the transformers, we remember, what do transformers transform? They transform voltage, they transform current, and they pass through the power. What is this third quantity that I didn't mention? I almost did. That they also transform, besides current, besides voltage. What is the other thing that they transform? Do we remember that? Can somebody pipe it in on voice? Or maybe type on the thing. I want some participation. Oh. Impedance. Evan, thank you so much. Yeah, transformers transform voltage, they transform current, and they transform impedance. Hence, we have something that is called impedance matching transformers, mostly used in audio. All right, there's a bit of a zigzag here. I wonder if you see it or not, or is it just on my screen? That just happened, and I can't get rid of it. All right, now we talked about the permeability. Okay, yeah. If somebody by any chance has access to drawing things on the, maybe there's some kind of a glitch in Zoom, just press Control E. That will give you the eraser, and just touch it with the eraser here. Maybe there's somebody that was accidentally had that. Okay, because I can't do that. It doesn't work. I get the blim thingy. I can get my pen, I can get my laser, but I cannot get my eraser. So, all right, probably a glitch. All right, relative permeability. The absolute permeability that we talked about, well, I'm introducing you to that new word, absolute permeability, is measured, remember the unit is henries per meter. But now we're going to talk about something that's called relative permeability. Instead of dealing with messy decimals, scientists use relative permeability sometimes. The relative permeability tells us how many times better a material is conducting the magnetism than an empty space. So how much better it is than a vacuum when it comes to conducting the magnetic field. And for example, iron is, well, some 5,000 plus, maybe 6,000, depending on what kind of alloy we're talking about. So it's about, about 5,000, 6,000 better in conducting, 6,000 or 5,000 times better than the vacuum or the air. So it would be something worth to notice. All right, relative permeability, and it's designated with the mu with the designation of R for relative permeability. It's the permeability of material compared to the permeability of vacuum. And do we remember what permeability of the vacuum is? Oh, there it is. The permeability of vacuum is 1.26 times 10 to the negative 6 henries per meter. Okay. So permeability of the vacuum is our base thing. So comparing vacuum to vacuum, if you put that into the denominator and denominator, we're going to have a number divided by the same number, which vacuum compares to a vacuum as 1 to 1. So we get the 1. Now the air is pretty close to the vacuum when it comes to magnetic field. So it's almost sort of like 1. And iron, which is ferromagnetic material, it's roughly 5,000 or more times. So that would be the relative permeability of an iron would be 5,000, 6,000, something like that. And here's the permeability, also known. So the permeability of a material, okay, so it was known also as the absolute number, the absolute permeability of the material, the real one, okay? Real permeability as a number. It's going to be with henries per meter. And permeability of a vacuum also is designated with henries per meter. So we get the same unit over the same unit. The units are going to cancel, so the relative permeability has no unit. It's just a plain number. Okay. We're getting towards the end. Let's go just do a quick calculation. This is a simple one. A certain grade of industrial iron has the relative permeability of 6,000. See, there's no unit. Calculate the absolute, whatever its permeability actually is, in henries per meter. What's the permeability? And you see there's no designation here. Of this iron here. Alright, so okay, that thing here has to be erased. Okay, there's a mistake here. Whoa, go back, go back, go back. Yeah, that should be just nothing here. Alright, that's the absolute permeability, which is this one here. That's the one here. Okay. So when we look at this formula here, from that formula we can derive this here, right? And which is going to be that. Plug in the numbers. The absolute permeability of this object is that permeability of the vacuum times the relative permeability, yeah, And that's going to give us about 7.56 times 10 to the negative 3 henries per meter. Just get yourself a calculator and just punch in the numbers to make sure. Last slide. Alright, problem 2. Imagine you have 3 identical sealed boxes. Let's say those boxes are made out of plastic, which is quite neutral. Paramagnetic material. Alright, inside each box is a different block of material. In one box there's copper, in the other box there's air, and in the third box is an iron. And then here's the question. If you pass a uniform magnetic field through all 3 boxes, maybe one at a time, which box will cause the magnetic field lines to tightly bend inward, just like inside the concentrating lens, and crowd the magnetic lines together inside of it? Anybody, just at the top of your head, which one would you have the gut feeling here? Somebody say something. Anybody? Anybody? Anybody at all? Okay, I'm not going to wait too much. We have copper. Nika, thank you. Well, thank you for being brave and saying something, so my hat off to you, but your answer is wrong. Alright, but thank you for speaking. Good, that's why we're in school. And we have iron. Anybody else? Alright, it is the iron actually. So here's my special effects. Okay, hold on. Boom. Alright, here's the box with iron. Iron is a ferromagnetic. Iron is ferromagnetic and has very high relative permeability of 5,000 plus. Iron acts as magnetic highway, actively attracting, bending, and concentrating the magnetic field lines inside itself. Air is paramagnetic. It doesn't care. It has sort of like a relative permeability of 1. And the copper is diamagnetic. It actually repels the lines. Its permeability, relative permeability, is less than 1. So what would the iron box do? It would do this. If you have, okay, here's my, if you have, let's say there's a north pole of certain magnet, and there is a south pole of a certain magnet, and we have those lines going uniformly distributed, okay, if nothing is there. And then you put the box with iron. Let me change the color. Oh no, we can. Okay, it doesn't let me. So, okay, same color. So if you put the box with iron here, inside that uniform here, right, those lines are going to kind of be attracted to that. So you're going to have all those lines kind of gathered from all around. They're going to try to pass through that thing here. So you're going to have a stronger magnetic field passing through that iron. Okay? And that is the lesson on the permeability. Well, it's pretty much scratching the surface, but now you should be comfortable with the idea of magnetic permeability. Next time we see each other, I also will try to give you some insights on the saturation that has to do with the permeability as well. They're both tied. It says that I got one new message. So does copper make a magnet field wider? It would repel those. It would work against. And yeah, it would just, yeah, Because you would fight it. So yeah. So when it comes to the saturation of ferromagnetic materials, because when we talk about saturation, we have to talk about ferromagnetic materials because we're magnetizing something. And in the lab that we're going to do, so I would let you do the lab first, so you get the experience of it, and then I will explain things. What is it that you did? What is it that you experienced? And what is it that, why did you get results as you did? Okay? So I will see you during the lab. Thank you for your attention, and enjoy the rest of the evening.